So as I promised, I'm going to do an example, actually two examples that involve using cylindrical coordinates and kind of demonstrating the power that they have. Just to remember what it is that we're doing, we're just integrating some function over a 3D shape, which means that function could have something to do with the heat an object gives off. It could have something to do with the temperature. It could have something to do with the probability of something. It could have to do with center of mass, right? It could be density function, could be all sorts of things. Whatever this function represents, right? That whatever application we're given, we can interpret it over our 3D region of integration. And so in this particular problem, we're evaluating a particular function. I guess I should have a dv here, dv, over the region bounded by y equals x squared plus z squared, and the plane, oops, that's not supposed to be a z, that is supposed to be a y. The plane y is equal to 4. So if we don't know what this looks like, right, this region of integration that we're trying to figure out, it's probably a good idea to try and sketch it, and I have prepared traces for us to do just that. So let's look at the trace when z equals 0. We get the equation y is equal to x squared, and last time I checked, that looks very much so like a parabola. Now, since there is no z on the xy plane here, this little slice, we have nothing else to sketch. So we're going to move on to what happens when we let, what do we get? Sorry, y, we forgot y equals 4. Y equals 4 is a thing, so let's include y equals 4. So y equals 4 is maybe somewhere up here, y equals 4. And that's going to intersect at the point 2, 4, and at the point negative 2, 4. Great. Awesome. And so, we have a region of integration. Okay. Now let's look at the YZ plane. So for the YZ plane, let's see, what are we going to see when we let x equals 0? Well, we're going to get y equals z squared, and that is a sideways parabola. And again, intersecting y equals 4 here. Okay, so what did we get? This is the parabola y equals z squared, and that is going to be our little region of integration, right? This is kind of just cross sections of our 3D object here. All right. Cool, great. Maybe I should do the points of intersection here. So if y is equal to 4, then z is going to be 2 here. Maybe I'll zoom in so I can. So y is equal to 4, z is equal to 2. And over here, if y is equal to 4, z is equal to negative 2. Awesome. All right. And so for last but not least, let's pick some y values for the xz one. So we don't want to pick y equals 0, because if we plug in y equals 0 here, we are just going to get x squared plus z squared equals 0, which is only true for 0, 0. So let's pick let's pick y as 1, right? So y is 1, that's a circle with radius 1. So that's y equals 1, all the way out to maybe y equals 4. So for y equals 4, that's a circle of radius 2. Maybe I'll make this one. Well, that's okay. So this is y equals 4. This is the equation 4 equals x squared plus z squared. Okay, so hopefully by now we have kind of an idea that as we increase the value of y, we're going to get larger circles. We look at parabolas in our cross section. So this looks like it's going to be some sort of paraboloid kind of facing in this direction. Okay, something like this. And it's cut off by the plane y equals 4, right? Y is equal to 4, okay? And so our region of integration for this shape is, right, this is going to be the body of this paraboloid. Okay, that is what we have to work with here. So kind of fill this in so we have a visual. Okay, and we know that these cross sections are all circular in nature, so cool. So the question is, how on earth are we going to trap this shape? Do we trap it using x, y's, and z's? And clearly since this is a section on polar coordinates, I'm going to suggest that we don't do that. right? And you'll notice that if we look at all three of these traces, this one right here looks like a bunch of circles, okay? And lo and behold, if you look at this right here, this is the circle, right? This is a circle. And that circle is what I drew in blue over there, x squared plus z squared equals 4, you know, at y equals 4. Okay, that's what that circle is. And so what we could do here, right, we could try and parameterize this in terms of x and y and z, but I'm going to suggest that what we can do is, all right, well, we want polar coordinates to kind of come into play here. And if you imagine rotating your view a little bit, we need to trap x, y, and z, but I am going to suggest that we create an r, that we create a theta, and then we need one more variable, okay? So let's just use the fact that our footprint for this humongous shape, right, our footprint, this projection, if you will, of our shape onto the plane y equals 4 creates a perfect circle centered at the origin. Now the difference is that normally when we do this, there's an x here and there's a y here, and we let x equal r cosine theta and y equals r sine theta. But here we don't have the xy plane, we have the xz plane. So what's going to change? Well, truth be told, not much. All we're going to do is we're going to say, look, if we let x equal r cosine theta, and we let z equal r sine theta, that right there is the parameterization for a circle centered at the origin of the xz plane, right? It's centered at the origin. Now, a lot of you might be thinking, well, how isn't that circle over here? Well, not quite, because we haven't specified the y value yet, right? If you just say let x equal r cosine theta and z equals r sine theta, you're right. Where is this circle floating in space? There's infinitely many of them. So that's why when we do this parameterization, eventually at some point, we're going to need to add something that controls the y coordinate as well, okay? So x equals r cosine theta, z equals r sine theta. Well, what is my r going to be? Well, this is a circle at its fattest point. This is a circle of radius 2, and we want to cover the entire circle, right? We want to get every single point, right, that is on this circle and above it going this direction, right? That's our goal. Okay, so r goes from 0 to 2, theta goes from 0 to 2 pi. Okay, fabulous. Now, what values are we going to do for y? Well, y, let's see. If we think about it, any y value we could pick going from smallest, right? Now, y doesn't just go from 0 to 4, because that's going to give us circles, like remember all of these circles that we just said, like this, right? That's basically saying we get all these circles of radius 2, and we just repeat them from 0 to 4. That, if we did 0 to 4 like this, that would be a cylinder, right? We'd be looking at a cylinder like this. And we don't have a cylinder, we have a paraboloid. So this just means that while our upper bound for y is clearly going to be 4, right? That's going, right? The upper bound for y is going to be 4. That's going to be where we get the largest circle. The lower bound, right? What is the lower bound for y? Well, the lower bound for y is any time that we're hitting this paraboloid, right? The lower bound is the paraboloid. So the paraboloid is described by y is equal to x squared plus z squared. Well, so let's just put that in. X squared plus z squared, right? That's our lower bound for y. Okay, so we're hitting the paraboloid every time. Now, for those of you who might be raising a red flag, yes, x squared plus z squared, not allowed to exist, right? Because we are no longer in x and z. We let x equal r cosine theta and z is equal to r sine theta. So if we scroll down a little bit, here's the parameterizations that we have. we have x squared plus z squared, which becomes r squared cosine squared theta plus r squared sine squared theta less than or equal to y less than or equal to 4. We have r less than or equal to 2, greater than or equal to 0, and we have 0 less than or equal to theta less than or equal to 2 pi. Using the parameterization x is equal to r cosine theta and z is equal to r sine theta, right? Using polar coordinates, but not for x and y this time for x and z. And again, you might notice, hey, wait a sec, can't I factor in r squared from this? Absolutely, because if you factor, r squared, we're going to get cosine squared plus sine squared, which last time I checked is just equal to 1. So everything here, we can basically say that the lower bound for y is simply just going to be r squared, okay, which is pretty nifty. So what does our triple integral look like? Our triple integral now becomes, triple integral is going to be triple integral, right, our function, square root of x squared plus y squared. All of our bounds are constants with the exception of y. So since y is not constant, technically I can put y anywhere as long as it comes before the r variable, because if I put it after the r variable, when we evaluate it, there's going to be an r still in our answer. So just to get it out of the way, I'm going to put it first. I'm going to put y goes from r squared to 4. Then I'm going to put r goes from 0 to 2. And then I'm going to do theta goes from 0 to 2 pi as the end. And so this is going to be dy. Now remember, we went to polar coordinates, so we still have to do this extra r and then dr d theta. Okay, that's what we have to do here. So we're not quite done, although we've made good progress. We are now almost all the way in cylindrical coordinates. The only thing that's left to do is the fact that we need to properly move this function from xyz land into r and theta land. So the way we do that is we're just going to plug in for x, we're going to plug in our r cosine theta. So our triple integral just becomes 0 to 2 pi, 0 to 2, r squared to 4, of the square root of r squared cosine squared theta plus y squared. All of that times r, and then dy, dr, d theta. This is our setup. And if we have a quiz or something like that, and you're wondering how many points you're going to get for doing this, a lot. If you get here, you're doing great, all-star, 8 out of 10 points minimum. Okay, like doing the integral is cool, but getting in this setup is really important. Now, I've only just realized a slight little mistake, which is that this function that we're integrating is actually not supposed to be plus y squared. It's supposed to be plus z squared. And that makes a slight bit of a difference because now we plug in, now we're going to plug in z is equal to r sine theta. And hopefully we know at this point what happens when we have r squared cosine squared plus r squared sine squared theta. Basically, the stuff inside our square root is going to become the square root of just r squared. And then we'll have a times r on the outside. So this thing just becomes r times r, which is, well, just r squared. So basically, putting this into cylindrical coordinates allowed us to get a triple integral of just r squared d, dy dr d theta, with our bounds still as r squared to 4, 0 to 2, and 0 to 2 pi. And this is actually fairly easy for us to solve, so that is wonderful. So I want to go on to one more example, which is basically, it looks something like this. It looks a little crazy, but the idea is that you might be given something that is already in x, y, and z coordinates. So for us, it's going to be -2 to 2. It's going to be negative square root of 4 minus x squared to positive square root 4 minus x squared, and then integral square root of x squared plus y squared and 2. And then what are we integrating? We are integrating the function x squared plus y squared dy, dz, dy, dx. Okay, so the idea here is basically to recognize that we have something that probably will work better in cylindrical coordinates than it will to evaluate it using x's and y's. And the giveaway is that we have a lot of x squareds and y squareds and stuff minus x squareds. And anytime in any problem we've ever seen number minus x squared or number plus x squared or x squared plus y squared, hopefully our first immediate thought was go to polar coordinates. So how we're going to approach that is we're just going to take a look at what this shape is. Okay, we're going to see what this is and see if we could parameterize it in a nicer way than the way that it currently is. So currently, what do we know? We know that x goes from -2 to 2 for this shape. We know that y goes from negative square root 4 minus x squared and positive square root 4 minus x squared. And then z is greater than the square root of x squared plus y squared all the way to 2. Okay, so let's take a look at these individually. I'm going to start with x and y because those are the nice ones. So if I'm trying to figure out what this shape is, okay, what shape am I seeing here? X goes from -2 to 2, right? So I can just pop that in, right? X goes from -2, or I guess that's +2 over there, -2 to +2, okay? So something like that. It's bounded by those planes, which I'm not going to sketch in their entirety. Now the y bounds, what are the y bounds of the shape? What is the y part of our domain? Well, let's see. This looks a little bit ugly, but what I can do is I can actually just square both sides, and I very quickly get 4 minus x squared is less than or equal to y squared is less than or equal to 4 minus x squared. And if something is less than or equal to and greater than or equal to something, that it can't be both unless it is equal, right? Unless they're both equal sign. So what this really is it's telling me that the boundary of this shape is 4 minus x squared equals y squared, which hopefully we recognize as x squared plus y squared equals 4, which is a circle. So what does that mean? That means, right, now kind of looking at it, it becomes a bit clear, oh, this is the upper half of the circle, this is the lower half of the circle, and the y gets to be any value between it. So I'm going to sketch kind of this region right there. Okay, so now I've covered my x's, I've covered my y's. Now I just need to see what is this z thing looking like? All right, so what is this? Well, this, if you don't know, it's a cone, but if we're not sure, we could do traces, right? We could say, okay, well, what does z equals the square root of x squared plus y squared look like? Right? Like what is this thing going to look like? Because I know what z less than or equal to 2 looks like, right? Z less than or equal to 2 is some plane up here at z is equal to 2, okay? So we just need to figure out what is z greater than. And what shape is this? Well, we can look at traces, and we notice that when x equals 0, we get z is equal to y, essentially. Then if y is equal to 0, we're going to get z is equal to x, which again are these straight lines, right? There's z is equal to y, and z is equal to x is right here. And then if we let z equals 0, well, we just get a point, so we don't want to plug z equals 0. So let's try like z is equal to, I don't know, 1. If we do that, we're going to get x squared plus y squared equals 1, which is a circle. So at z equals 1, we're basically getting, we're getting a circle. And those circles increase in size. Like if z is 2, we're going to get a circle of radius 2, right? We're going to get x squared plus y squared equals 4 for z is equal to 2. And so this actually ends up being a cone, so let me draw this just a little bit nicer. So what have we found out about this shape? Okay, we have found out that z is trapped by this cone. Okay, it has a lower bound. Has a lower bound of the square root of x squared plus y squared. It has an upper bound at z is equal to 2. It casts a shadow. It projects onto the xy plane in the shape of the circle x squared plus y squared is equal to 4, which should make sense. Because that basically tells us that this circle that's on the top, right, the intersection, right, the intersection of our cone, which is the square root of x squared plus y squared, and the intersection of that and our plane, which is z is equal to 2, yields the result square root of x squared plus y squared is equal to 2. And if we square both sides, we get x squared plus y squared is equal to 4. So that kind of tells us that, okay, look, so the top of this is basically the same circle. So where is our region of integration? Our region of integration is greater than this cone, less than the plane, over all the x and y values that fall inside this circle, right? This shape is kind of projected onto the xy plane. So it covers all of these xy values, okay? Every single xy value here corresponds to some appropriate z value, right? Inside this shape. And so the question is, how can we take what we were originally given, which was this, and redo it into polar coordinates? So now that we kind of have this, I'm going to make some space. Oops, if I can find the eraser button. I'm going to make some space, and I'm going to do it up here because that way we can kind of see what the original equation is. All right, and now we're going to do this in polar coordinates. And I know for a fact that I want to use x is equal to r cosine theta and y is equal to r sine theta, because my z value is just basically going to be any z that goes from this cone up to the lid, to z is equal to 2. And my x and y values are basically coming from that circle, right? It's coming from the circle x squared plus y squared equals 4. So I'm going to use that parameterization, and we're going to let r go from 0 to 2, and theta goes from 0 to 2 pi. Okay, so that's our parameterization for the x and the y coordinates. So now all we need to do is to figure out what z goes between, but z goes between the square root of x squared plus y squared and 2. But luckily, x squared plus y squared in polar coordinates, that's just r squared. So we really have z is greater than or equal to r and less than or equal to 2. All right. So what we've basically done at this point is our new triple integral in polar coordinates involves z is going to go from r to 2. We're going to get theta goes from 0 to 2 pi, and r goes from 0 to 2. Now the function we're integrating is x squared plus y squared, but again, when we plug in our parameterization for x squared plus and y squared, we're just going to get r squared cosine squared plus r squared sine squared, which factors out to just become r squared, right? We're going to get r squared cosine squared theta plus r squared sine squared theta. We can factor out an r squared. We get cosine squared theta plus sine squared theta, and this is equal to just 1. So really, we just have an r squared here for our function. Now what happens to our dv? Well, our dv becomes, let's see, our z stays the same, so dz. But then because we introduced r and theta, there's a times r, and then times d theta dr, and that makes up our new dv, right? This is our, the entire thing is our new dv. And of course, we would multiply the r's together to get r cubed, and then go about doing some integration. So the key thing with cylindrical coordinates, right? The key thing is we're looking at shapes that cast shadows in some direction that basically have a domain, right? Where part of their domain creates the shape of a circle. So we can use polar coordinates on that and then just let the rest of it be its normal good old self from something to something else. So we're talking about when we're doing paraboloids, we're talking about when we're doing cones, we're talking about when we're doing cylinders, anything like that, when it intersects with another object, whether it's a plane, right, or some sort of curve or a paraboloid inside of a paraboloid, whatever it is, when it casts a shadow of a circle, or an ellipse or something like that, we should immediately think, okay, we're going to go ahead and use polar coordinates and to do this, aka cylindrical coordinates, now that we're in 3D. So that's going to do it for these examples. Two kind of very quick examples. The textbook has a bazillion more, and there are 8,000 examples you can find if you just Google cylindrical coordinates on Google. So go ahead and check those